In this video, we're going to talk about the line of best fit, which is an application of least squares. So the line of best fit shows up all over the place. It shows up all over the place in math and statistics. Okay, so I want to motivate how we're going to find a line of best fit with an example. And then afterwards, I'll state the general formula. So let's do this example where we try to find the best fit line of the form y equals, so this symbol here, it looks like a B, is the Greek letter beta. And one of the things that distinguishes B from beta is the fact that beta sort of has this, tail. It sort of extends downwards like this. So this is beta naught plus beta 1x. Okay, so I want to find a line that looks like this, that has this form. And this needs to sort of fit the points 0, 1, 2, 3, and 3, 3 in the best possible way. All right, so let's draw a picture, and then we'll talk about, well, how are we going to get this line? All right, so all my points are in the first quadrant, so I'm going to draw a picture where I just sort of focus on that first quadrant. Let's draw some tick marks, so 1, 2, 3. So this is 1. And in the y direction, let's go 1, 2, 3. And now let me draw the points in. So we have a point at 0, 1. We have a point at 2, 3. So we have a point at 2, 3. And then we have a point at 3, 3. So there's a point at 3, 3. And what we want to do is we want to find a line that sort of best fits these data points. So clearly I can't draw a line that's going to go through all three of them. And it might not even be the best thing to draw a line that goes through two of them. I want to sort of draw a line that comes like as close as possible to all three in kind of a rough sense. So I'm just going to draw a rough sketch of what that might look like. So maybe it looks something like this. I don't know, let's draw that a little bit better. Maybe it looks something like this. No, one more time. I don't like that. Something like this. Okay. I just want to give myself a little bit of room between the line and the points. But let's say my best fit line looks something like this. So this is y equals beta naught plus beta 1 x. Alright, so one of the most common ways to find this best fit line is to look at each of these points that we sort of have, these data points, these points that we observe, and compare that to the points on the line that are directly either above these points or directly below. So for 0, 1, the point that's sort of directly above it on the line is here. For 2, 3, that point would be directly below, it would be here. And then for 3, 3, it would be directly below, and that would be here. And of course, ahead of time, I might not know whether these points are above or below. And of course, that sort of also depended on my picture, but it's not going to change the explanation, so it's fine for me to draw it like this. So now let's write down the coordinates for each of these points. So for this first green point above 0, 1, its x-coordinate is still the same, it's 0. And the y-coordinate we'd get by plugging 0 in for the x in the equation of the line. So that would give us beta naught plus beta 1 times 0. And yeah, it's true that beta 1 times 0 is just 0, but I'm going to keep it in this form so I can see the general formula later. So similarly for this next point, its x-coordinate is 2, and the y-coordinate would be beta naught plus beta 1 times 2. And this last point, x-coordinate is 3, and the y-coordinate is beta naught plus beta 1 times 3. Because that's what I get when I plug 3 into this equation. So what we're going to do now, our technique, the most common way to find the best fit line is to do the following. We're going to look at the distance between each point on the line and each observed data point. So I'm going to look at this vertical line, this vertical distance, this vertical distance. So this vertical distance is called a residual. So this first residual, I'll call this R1. The second residual, I'll call this R2. And the third residual, we'll call this R3. So the most common way to find the best fit line is to minimize the sum of the squared residuals. Okay, so what does that mean? Well, that means take R1, square that. Take R2, square that. Take R3, square that. And look at the sum, and then we're going to try to minimize this. So the fact that we square all of these, so that'll mean that when we subtract these 2 points, it doesn't matter whether we end up with a positive number or a negative number. When we square it, we overall just care about, well, what's the distance? So now let's compute this sum of the squared residuals. So if we do that, so if I figure out what R1 is first, so to figure out what R1 is, I got to take these two y values and subtract them. So that would give us, so B0 plus B1 times 0, and I guess technically I should say beta. Sometimes I get a little bit sloppy and I'll say B instead of beta, but beta is here, and then I subtract that from 1, which is the other y value of this bottom point, and then I need to square that, and that's R1 squared. So this right here is R1. And now let's do the same thing for R2 squared and R3 squared. So R2 squared in the same sort of way. I'm going to stick to this same format. I'll do beta naught plus beta 1 times 2 minus the other y coordinate, which is 3. That's from my data point. Square that plus, and then R3 is going to be, well, beta naught plus beta 1 times 3 minus its y value on that's actually observed, the data point. That's the 3. And then we square that. So this is our sum of squared residuals. And we might notice, looking at this, that this looks like just the square of a bunch of entries. This kind of looks like the length of a vector. And that's exactly how we're going to rewrite this. This is actually the length of the following vector. So I'm going to try to give myself a lot of space. So the fact that we're subtracting things means it's the length of some vector minus some other vector. Okay, so the first vector is, so the first entry is beta naught plus beta 1 times 0. And then the first entry of the next vector is the 1. So notice that that's exactly where this part comes from. The second entries come from this second term here. So it would be beta naught plus beta 1 times 2, and then minus the 3. And the next set of entries would be beta naught plus beta 1 times 3, and then minus the 3. And of course, this is actually the length squared. If we didn't have the squared here, when we figure out the length, we'd have to put a square root on this whole thing. Okay, but now this is starting to look more promising because it's starting to look more like matrices and vectors. Before, it didn't look like that at all. All right, so next, what we can do is we can rewrite this into a matrix format. This will end up being the matrix 1, 1, 1, 0, 2, 3. So we're sort of taking the coefficients of all the B0 terms first. Those are all the ones. Then the coefficients of the B1 terms, the 0, 2, 3. And that gets multiplied by the vector B0, B1. And I could see that because when I multiply this matrix times this vector, we form a linear combination of the columns where the weight of the first column is B0. And that's where we get the B0, B0, B0 from. And the weight of the second column is B1. And that's where we got these other 3 terms from. All right, so that minus the vector 1, 2, 3. So we want to figure out the length of this. We want to minimize the length of this squared. So this matrix right here, let's call this A. This vector, I'll call it X. And this other vector, the 1, 2, 3, I'm going to call that B. So what we're trying to do is actually minimize this. Minimize the distance between B and A times X. And that is a least squares problem. So a least squares problem. And that's pretty cool, I think. We've converted this geometric problem of finding this line of best fit to a matrix problem. where we try to find a least squares solution to this. Okay, so I'm going to go kind of quickly through the least squares process because at this point we've already seen some examples in the previous video. So if we want to find the least squares solution, first we'd compute A transpose times A, and I've gone ahead and done that, and that gave me the matrix 3, 5, 5, 13. All right, and I've gone ahead and computed A transpose times B as well, and that ended up being 7, 15. So at this point, we're ready to set up our normal equations. And when we do that, we get the equation 3, 5, 5, 13, so that's A transpose times A, times this vector x hat that we're trying to find, equal to 7, 15. All right, so now we want to solve this. So in the previous video, the way we did this was by row reducing. But in this problem, row reduction looks tedious. It's definitely doable, but we'll for sure, I think, get fractions here, and that seems to be hard to avoid. So another way to go about this is, if this matrix ends up being square, and it's invertible, we can use the inverse. In fact, it'll turn out actually that A transpose A will always be square, but it's not always going to be invertible. But in this case, it is. So we can use the inverse. So let's figure out the inverse of 3, 5, 5, 13. And we have a formula to find the inverse of a 2 by 2. It's 1 over the determinant. So 1 over 3 times 13 minus 5 times 5. And then you multiply it by the 2 by 2 matrix, where you switch the 3 and the 13. And then the other two terms, you just switch their signs. So you get -5, -5. All right, so now evaluating the determinant, we get 1 over 39 minus 25, so that's 14. So 1 over 14 times the matrix, 13, -5, -5, 3. All right, so at this point, we're ready to isolate x hat. So to isolate x hat, we take this equation and multiply both sides by this inverse. So here's the inverse on the left. So doing that, it'll cancel out this matrix over here, and we'll be left with x hat on the left-hand side. On the right-hand side, we'll have the inverse of 3, 5, 5, 13. So the inverse of this being multiplied by 7, 15. All right. So let's write down what the inverse was. The inverse was 1 over 14 times the matrix 13, -5, -5, 3, and that's multiplying 7, 15. All right. So now working out this multiplication, we get 1 over 14 in front. And if we multiply these, so I'm going to go ahead and do this quickly, we'll end up with 16 first and then 10 after that. And now we can go ahead and distribute it in 1 over 14. So 16 over 14 becomes 8 over 7. 10 over 14 becomes 5 over 7. All right. So if we zoom it out a little bit, so we can see what this represented. So this represents my solution, x hat. But in the best fit problem, remember x hat was this vector, beta naught, beta 1. So that's what these two entries represent. The 8/7 is the beta naught in the equation of my line. 5/7 is the beta 1. So now let's go ahead and write down the equation of our line. So I've just copied down the vector from before. So our best fit line now, its equation would be y equals, first I write beta naught, 8/7, that's our constant term, plus, and then beta 1, 5/7 times x. And that's the best fit line for our data. So the method that I showed, it generalizes. So I'm going to end by just stating a formula that is true in general. So in general, if I want to find a line of best fit, so something that has this form, y equals beta naught plus beta 1x, for the data points x1, y1, x2, y2, ... up until xn, yn, what that means is we want sort of the best solution, sort of the best approximate solution. The best approximate solution to the following. So if I take this first x coordinate, x1, and I plug it into the equation of my line, we would get beta naught plus beta 1 times x1. And ideally, we'd like that to be equal to y1. So it may not be equal to y1, but ideally we'd like this. And in the same way, now if I plug in x2 into my best fit equation, we'd get beta naught plus beta 1 times x2. And ideally, we'd like that to be equal to this y coordinate. We'd like it to be equal to y2. And if we keep going like this, plugging in xn, we'd get beta naught plus beta 1 xn, and we'd like that to be equal to yn. So we're trying to find a best approximate solution to this system of equations. So if I have a system of equations, we can rewrite this in matrix form. So in matrix form, what we'd get is, so our variables here, first off, are actually beta naught and beta 1. Those are actually our variables, because all the x's and all the y's are the data points, and those are given to us in the problem. So the first column of our matrix will be the coefficients of beta naught, and those are just all 1. So 1, 1, dot, 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 up until 1. The next column will be the coefficients of beta 1, and that is x1, x2, dot, 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 up until xn. So we have this matrix times the vector beta naught, beta 1. That's what the left-hand side is. And then the right-hand side will be the vector that has all the y's as the entries. So y1, dot, dot, dot. Let me also write y2, actually. So y1, y2, dot, 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 up until yn. Up until yn. And in this system right here, this matrix is our matrix A. This vector is our vector x. And this vector of all the y's, this is our vector b. So what we try to do when we find a line of best fit is we want to find a least squares solution, a least squares solution to this. And when we do that, that will give us our line of best fit.